Hello everyone. We are standing on the moon here. An asteroid from outer space comes in and crashes into the lunar surface, kicks up a lot of lunar dust. In the background is our beautiful Earth. Despite all the excitement, we do want to get back home safely. This is a typical asteroid crash that happens on the moon very often. In reality, there won't be any flame when something crashes into the moon. Here is a stunning visual of a gigantic asteroid flying on a path close to the moon. In this numerical, we have to find the gravitational force of attraction exerted by the moon on the asteroid at two different distances, and also the acceleration of the asteroid towards the moon and that of the moon towards the asteroid. We take a look now at Newton's law of gravitation. m1 is the mass of object 1, in this case asteroid. m2, the mass of the second object, in this case moon. R is the distance between the center of asteroid and center of the moon, not between their edges. Therefore, the gravitational force is proportional to m1 into m2, also proportional to 1 by r squared. So F is proportional to m1 m2 by r squared, and therefore the constant of proportionality is g, which is a universal constant valid for Earth, Moon, Mars, and any other place on the universe. Here I want to show you a very important diagram where the asteroid can follow three different trajectories. If it goes along that red dotted line, it will crash onto the Earth and maybe burn during the entry into the Earth's atmosphere. If it goes along that blue trajectory, it will miss the Earth, and that would be a great contribution of the moon by exerting gravitational force and deflecting the asteroid's trajectory so that it doesn't fall on us. The third option is the orange trajectory, where the asteroid crashes directly onto the moon's surface, creates a crater, which is okay for us, and the moon has saved us from another hit. The beauty of the gravitational force is that it helps deflect these asteroids. Quick word about point masses before we jump into the numerical. In Newton's equation, m1 and m2 were defined as point masses. And Newton explained that large spheres like Moon, Earth, which are symmetrical, can be considered as point masses, and especially when the distances between the moon and some other thing like the asteroid is large. The asteroid is a jagged piece of rock, and it's not a sphere and has no symmetry. Still, it can be considered as a point mass because it has a large distance from the moon's surface in this particular case. The real true point masses in space are black holes, where large stars collapse into themselves, so they get a near zero volume, infinite mass, and infinite gravitational force F. That's when R becomes zero. Let's now get into the numerical itself. As we can see, we have to find gravitational force at two distinct distances, and we also have to find the acceleration of the masses towards each other. Imagine this sketch where we have the asteroid's trajectory shown along the yellow dotted line. The numerical gives a distance between asteroid center and the surface of the moon, which is 3000 kilometers. The moon's radius is known, that's 1737 kilometers. So we can find the distance r by just adding them. It's important to imagine this well so that we can solve different numericals using the right center distance. This is the indexed sketch when the asteroid moves closer to the moon, and you can see that the distance between asteroid center and the moon's surface is shown as 1000 kilometers. The radius of the moon is the same, and therefore the center distance r is equal to 1737 plus 1000 equal to 2.737 kilometers. The moon's gravitational This is the indexed sketch when the asteroid moves closer to the moon, and you can see that the distance between asteroid center and the moon's surface is shown as 1000 kilometers. The radius of the moon is the same, and therefore the center distance r is equal to 1737 plus 1000 equal to 2.737 kilometers. The moon's gravitational attraction causes the asteroid to slightly change its trajectory to even closer to the moon. Speed of the asteroid doesn't matter at all. The Newton's equation only considers mass and distance at a given point in time. We do the calculation, take all the 10 to the power terms on one side and the other terms on the other side, and we get a value of the gravitational force F is equal to 0.327 into 10 to the power 4 Newton. It's not a very big force, but since there is no atmosphere around the moon and just a vacuum, this is enough to cause a change in the asteroid's trajectory. Now we find the acceleration. We know the force of attraction, we know the mass, so we can find the unknown, which is the acceleration. So plug in the values of F and M1, and we can find out A for the asteroid. Similarly, the moon is also attracted towards the asteroid by the asteroid's gravitational force of attraction. F is the same between the asteroid and the moon. We just have to plug in M2 instead of M1, and we can find the acceleration of the moon. Obviously, the acceleration of the smaller mass is much higher, and the acceleration of the large mass of the moon is very, very negligible. We now do the calculation for the new distance as the asteroid gets closer to the moon. Plug in the value of r. Using the same equation, we find the gravitational force has increased considerably to 0.981 into 10 to the power 4 newtons. This force is good enough to slightly change the orbit of the asteroid. If that orbit gets changed in such a way that the asteroid won't hit the Earth, then that's a great achievement by the moon. This slide shows a simple calculation of acceleration using Newton's second law of motion. The force is already calculated for the distance r. We have two cases of r, and when we put that force, the acceleration of the asteroid will depend upon its mass m1. The acceleration of the moon will depend upon its mass m2, and we can see here that the acceleration of the asteroid is much higher than the moon's acceleration towards the asteroid, which is extremely negligible. Here is the calculation of the accelerations for the case 2 with the closer value of r. We can see that the acceleration has increased a lot, and the acceleration of the moon is also increased, although it is still extremely low. In this summary slide, we can compare the accelerations between the case 1 distance and the case 2 distance. The ratio of the r values is 1.73, and if we take a square of that, 1.73 whole squared will be equal to 2.995, and therefore the force has increased 3 times between case 1 and case 2. It only means that as two bodies come together, the force is proportional to 1 by r squared. So as r decreases, the force increases exponentially. Thank you. If you like this video, do subscribe to our channel and feel free to share it with all your friends. If you want more complex problems to be solved, do let me know, and I'll try to do that in my subsequent videos. Thank you and have a great day.